All right, so in the previous video, we talked about systems of linear equations, and we solved a few of them using the techniques that you would have learned in an Algebra 1 class. Elimination primarily, with some substitution in there. However, in this class, we're not going to tend to use that approach. A lot of the systems we look at will have even more variables and more equations to deal with, and that approach gets very, very messy, very difficult in those cases. So what we're going to use is an approach that's much more organized and eliminates the need to keep writing variables. So what we're going to start with is this discussion of what an augmented matrix is. Suppose we're given some linear system, some m by n linear system, so m equations, n variables, like this one. Okay. Now, if you notice the way that these systems are aligned, all of the x1s appear in a column, all of the x2s appear in a column, and so on and so forth. Really, what matters when we're doing elimination is the coefficients. If you go back to the previous examples, for example up here, in order to eliminate this x variable, I needed to have my coefficients opposites of each other, 4 and -4. The x, even though that's what we're solving for, you can kind of just think of it as a placeholder for that coefficient. So that tells me that if I can just eliminate the need to write these unknowns all the time, I can get a slightly more efficient method for solving these equations. That's what the augmented matrix is. What we do in an augmented matrix is we take all of the coefficients on our x1s and we take the arrangement of them as a column and actually put them as a column in what we call a matrix. We're going to talk about matrices in more detail in section 1.3, but right now I'm going to be using that term for what we're talking about here. You'll see all of the x2 coefficients showing up as a column here, and so on and so forth. We go all the way until we get to the xn coefficients, which are showing up here, and then we go one more column for the constant terms that each of these are equal to. Oftentimes when we're solving augmented matrices, you'll either see your matrix written this way, or occasionally you'll see a vertical bar put here, which symbolizes the equal signs here. And that's kind of just a visual thing to help you keep track of what's what. Okay. Now, how do we use these when solving systems of equations? Well, we're going to talk about row operations. These are what we do with augmented matrices. So when you're solving a system of linear equations, there's a few operations, 3 in particular, that you're always allowed to do. Any equation in a linear system can be multiplied by a non-zero constant, and we've done that. Over here, we multiplied our first equation by 4, a non-zero constant. What we got was an equivalent equation to the first one. Equivalent in the sense that these two equations have the same graph or the same solution sets. Okay, so that's a valid operation. Another thing you can do is interchange two equations. Now, we didn't have a need to do that in any of our previous examples, but it's very clearly a valid operation. I could have taken these two equations and flipped them. I could have written this one up here and this one down here. That's what I mean by interchanging. Nothing changes about the equations, just the order that I'm seeing them in. That's the only thing that changes. So that's a valid thing to do with the system of equations. And then finally, and this is what makes elimination work, you can add a constant multiple of one equation to another. Again, we did that here. By multiplying this equation by 4 and adding it to this equation, I got this equation that resulted, and this is the one that told us there was no solution. It's a little bit more apparent seeing that here. So I multiplied this equation by -2 and then added it to the next equation to get this one. I then replaced this second equation with the new one that I got from performing that row or that operation. So those 3 operations that we do in systems of equations can be translated into the equivalent operations on an augmented matrix. So in this augmented matrix right here, because each row of this augmented matrix represents one of the equations from our system, I can do any of those 3 operations on a row. For example, I can pick a row, multiply it by a non-zero constant. That's a valid thing to do with an augmented matrix. I can multiply a row by a constant and then a non-zero constant, and then add that to another row, replacing that old row with the new one that I got from doing that operation. I can also pick any two rows in this augmented matrix and interchange them, swap their positions. Those are called elementary row operations. We use elementary row operations to solve systems of equations that have been represented by augmented matrices. So let's see what that looks like. Right here, I've been given an augmented matrix, and I've been given a system of 3 equations in 3 unknowns, and I want to solve this using an augmented matrix. The trick here is to represent our matrix using just the coefficients that would appear in these columns. So for my x's, I have 1, 2, 2. 1, 2, 2. For my y's, 3, 7, 5. 3, 7, 5. For my z's, 2, 7, 2. And then I'll go ahead and use this bar notation here, 2, -1, 7. Okay. Now in section 1.2, we're going to talk in much more detail about this process, and I'm going to introduce more notation than I'm going to use right here. Right now, I'm going to put a little arrow, but in that section, we're going to write some stuff up here above our arrow that indicate what operations we're performing to get from this step to the next. Here is my goal with this augmented matrix. What I would like to do is get zeros below the 1 in this column. That's the first thing I'd like to do. And I want to make these zeros appear by using whatever row operations we've talked about up above that would do that for me. So, for example, if I were to take this first equation and multiply it by -2, and then add that to the next one, I said equation. I should be calling this a row at this point. So multiply my first row by -2 and then add that to this row, replacing the second row with whatever I get in that process. That would definitely produce a 0 here because I'll get -2 plus 2. My first row is not going to change. 1, 3, 2, 2. That stays the same. But if I imagine multiplying this by -2 and then adding, I'll get a 0 here. -2 times 3 is -6. Add that to 7, and I get 1. -2 times 2 is -4. Add that to 7, and I should get 3. -2 times 2 is -4. Add that to -1, and I should get -5. I want to do the same thing to produce a 0 down here. Turns out I also have a 2 down here, so the same row operation would get me what I want down here. Multiply this by -2. Add it to this row, and replace this row by the result. So -2 times 1 is -2, plus 2 is 0. -2 times 3 is -6, plus 5, -1. -2 times +2 is -4, plus 2, -2. And -2 times 2 is -4, plus 7, that's 3. Okay, so notice my first goal has been reached. I wanted to put zeros beneath this 1 right here. The next goal would be to get a 1 here. Ultimately, what I want is to get 1s along this diagonal right here. We're going to call that a main diagonal. That terminology is not really going to be important until section 1.3. But I'm aiming to get 1s along this diagonal. In that process, I would also like to get zeros underneath each 1 that I produce. Now, it just coincidentally and conveniently turned out that this already is a 1. But if it weren't, if it were like a 5 or something, then I can multiply this entire row by, in that case, 1/5. That would produce a 1. I just don't need to bother with it here. Okay, so the next thing I need to do, since I already have a 1 here, is produce a 0 beneath it. So nothing's going to change in my first 2 rows. 1, 3, 2, 2, 0, 1, 3, -5. Okay, but notice if I were to simply add this row to this one, it's all set up already for eliminating this and making it a 0. So let's add. 0 plus 0 is 0. 1 plus -1, 0. That was the goal. 3 plus -2, 1. -5 plus 3, -2. Okay? It, again, conveniently worked out for us that this final number down here was a 1. But if it came out to something other than a 1, then I would need to multiply this row by whatever the reciprocal of this is so that it becomes a 1. That would just require one additional step. Okay, now we'll talk about this term in the next section, but what we have here is an augmented matrix in what's called row echelon form. Row echelon form means that we have these ones along this diagonal and zeros below it. In section 1.2, we're going to talk about Gauss-Jordan elimination, which is the process of putting an augmented matrix in reduced row echelon form. What that would require is us to go back through and try and produce zeros above the ones as well, so that I have zeros everywhere except for this diagonal where I have ones. We don't need to do that to solve this system, however. So I can actually stop here and then think about what these what these rows represent. Remember, this third column here is my z column. So what is this equation? 1z equals -2, or z equals -2, right? I already have a solution for z. Now, if I rewrite this second equation, it represents y plus 3z equals -5. But I can substitute the -2 that I got for z here into this z and use that to solve for y. Y plus 3 times -2 equals -5. That's -6. If I add that to both, if I add 6 to both sides, I'm going to get y equals 1. Okay, now I have a solution for z and a solution for y. I can get x by going up to the... Oh, I just realized I was writing off the screen. There it is. That's what I was just talking about. I can use this third equation up here, which is x plus 3y plus 2z equals 2. That's what this top row would represent. Plug in the y and the z that I just got. X plus 3 times 1 plus, what do we say, 2z, so 2 times -2, equals 2. Solve this for x, which again, I'll let you fill in the gaps here. X is going to come out to 3 in this case. And now I have a solution to my linear system. So I get this ordered triple, which looks like 3, 1, -2. Okay? Now this process, by performing these row operations and getting this augmented matrix in that row echelon form that I talked about, is something we're going to talk about more in section 1.2. But if you choose to stop reducing this matrix at this point and then solve the way that we did here, this is called back substitution. Back substitution because we're starting from the bottom row and working our way towards the top. We're working backwards. So we get a solution for our last unknown, plug that into the equation above it so that we can solve for the next to last unknown, and then so on and so forth. So that's it for section 1.1, and next up we'll talk about Gauss-Jordan elimination, which is expanding on this process.